So today I'm going to introduce you to what is essentially the culmination of 3 years of research for me. I mean, flat out 3 years, right? And then I approach these things from really two angles overall. The first is my career as an IT generalist, right? I've been in IT for a few decades, and within that, early on in my career, I had a mentor who was a CFO, but he came up more on the tech track. And then within that, one day early on, he was talking to me and he lamented about the fact that he was the only person within the organization that actually understood like how all of the pieces of the software work together overall, like how it all fit. And like to me, I was like, well, yeah, that's why you're the CFO, right? Yeah, I was young in my career and early, but then I pondered that for a long time, and then I realized like the bad position that he was in, but then also to the rare position that puts someone in, right? Like most people build up a career with and they specialize in a specific software, a specific track, like our society overall is built around specialization, and then so there's a skill like if you can become like jack of all trades, master of none. But if you can master of all trades is like a huge, like that's where you become sea level, right? And then so within that, I built my career kind of on that level, right? Becoming the person that can actually understand those systems. And so within like Fortune 500s and big organizations, it becomes complex, right? There's very few people that can actually understand and have direct experience with that complexity of a multitude of systems working together. And then so it becomes a huge asset for a person to have. And then within that, I just built that on top of what I've done my whole life, which is engineering, right? And then I just, to me, if I try to understand something and I want to understand something, I just take it apart and reverse engineer it, and then I put it back together. And I keep doing that. And if I can put it back together better than it was before, then I've like mastered that concept overall. And so when I combine these things, about 3 years ago, I start focusing heavily on AI. And then what I realize is that AI is not actually learning from your data set. And I've gone over this like in a multitude of different ways now, right? Essentially, AI is learning on abstractions of your data set. And then it's learning on, essentially, the bottom line is that within any data set, there is a shape that exists, right? And this is a big known factor within topological geometry, quantum physics, etc., which is why like all of my interests gravitate towards those areas, right? Like my interests like culminate, and it seems broad and across the board, right? Like genetic algorithms, quantum physics, hyperdimensional computing, topological geometry, and these seem like all swarm algorithms, and these seem like all disparate parts, but to me, looking at a map, they fit together, right? And then they fit together in what we're going to look at here, which is the Zyra class of models. And then so the Zyra class, Zyra isn't just one model, and this isn't the first model of Zyra, okay? And then before we dive into the model specifically, I also do want to mention that this does come with like very specific mathematical grounding. And then we released this research paper, Ryman-based information extraction, or RBIE. At the moment, as of the making of this video, there's only one place where this is published, so I'll leave a link to that in the description of this video. And then you can look through if you're very interested in like the full mathematical grounding. Here it is. Here's the nice research paper there. Going back to the model very specifically, so the Zyra suite of models is Zeta-inspired AI geometry models. So they are built upon AI geometry principles and resonance-based learning dynamics, utilizing insights from Ryman Zeta zeros as the foundational spectral filters. If you're not familiar with that, essentially putting that into like simplistic terms, so Ryman zeros and the Ryman hypothesis states overall that there's a real part of zero and an imaginary part of zero. Think of the real part of zero as an anchor point, right? If you know what the real part of zero is and then where the real part ends and the imaginary part begins, you can use like that as an anchor point for any measurements that you would ever want to do, specifically any distance measurements. Secondarily, there's another factor that goes into that, which is that not only is that edge boundary and anchor point that you can measure from, but the imaginary part of 0 functions differently than the real part. So the real part is like an anchor, whereas the imaginary part is like a rotational axis. And then so data rotates around the imaginary part of the 0, basically, is like how that kind of works out. And then so the bottom line is that by analyzing the distribution of these imaginary parts, you can extract structural information embedded within what appears to be noise, this like the learning process. And then so once this frequency structure is understood, then the signal can be projected back onto the real axis, filtering out the oscillatory noise and retaining only the core informational signal. Putting what I'm going to show you here into like as simplistic terms as I possibly can, we have been training AI models backwards, right? And so we train AI models according to labels of data, and then which is a human construct. Let's take fashion mnist as a particular example, right? Fashion mnist is classified and categorized into 10 categories, and then it's like of clothing. So it's like shoes, pants, purses, handbags, like etc. Right? But within that, one, those labels are a human construct, and then two, there's a lot of variation, if you think about it, between some of those, and less variation between others. So a good example would be pants, right? There's not a lot of variation of pants. There's not a lot of ways to vary the shape of pants, and what pants look like overall. Compare that to shoes. Shoes, you have sneakers, high tops, high heels, like women's shoes compared to men's shoes, running shoes, basketball shoes, like all different types of shoes, right? And they're going to be like different sizes, different shapes, different structures. Like there's a ton of variation in shoe compared to the low variation within pants, but both are this human construct label of pants versus shoes. And then those are arbitrary labels, but then when you look at the actual signal of that, the shape of that, the shape of shoe is far more complex than the shape of pants, right? There's just so much more complexity that can go into shoe overall that can go into pants. And then that matters when you're training a neural network and an AI that's how their brain works, right? That's what they do. They go through and they look at first the shape of the data and then the labels. So what my process does here is very flat out and simplistically say we're doing it backwards, right? We're saying first go towards and learn these arbitrary labels, which we've just established are 1,000,000% arbitrary, and then figure out what to do from there, right? And then that's backwards. And then so what my method is figure out the actual shape of the data set. So in this instance, fashion mnist, right? That has a shape to this model, and the natural shape of fashion mnist to the model is not going to match the labels. It's going to be very different than the labels, right? But so step one, we say just learn the shape. Learn the shape however you want to learn the shape. I don't know what the shape is, right? But go figure it out, and then that shape is then your ground truth, right? And then so whatever it is, you learn that as the ground truth, and that's your anchor point. And then from there, we're going to put these labels on it, right? We're going to put labels called pants. We're going to put another label called shoes. We're going to put another label called purses, etc. And I'm going to drop these items into those labels. Now remember, those labels are a human construct. What I want you to remember is most important is whatever the actual shape is that you learned, that's your ground truth. So in the end here, what you'll see is we're going to freeze the weights. The weights will, like, whatever you learned as the shape, that's the shape. Now, here's the labels on top of the shape. Measure and understand and learn the difference between the two, and then we're going to test you on that. And then so you'll be able to ground your understanding of these labels based off of what is real to you. And so it's first of all, like, it's very simplistically having the model understand and then translate that into human language. And that's, like, I mean, it's literally the process that we're going through here. So let's go through that process, right? So the very first thing that I do in this instance is I set this up. And then so in this first instance, I want to, like, make sure that I can actually do this, right? That the model can actually, like, train on this imaginary, shape itself, right? But the shape is actually the real shape. And then so in this instance, I'm training essentially what we call here like the Zeta CNN. It's utilizing the Zeta zeros. As opposed to just a standard CNN network. And then in this instance, it was taking forever to train, honestly. But so I can see the loss and 92% accuracy with this, which is going to be, I know it's better than the CNN, because I've tested a lot of CNNs. So it comes out about 4% better than a standard CNN. So this tells me that just basically building a model that's based off of our, like, the hypothesis in this research paper, right? It works. The math checks out. Cool. If I just plug this math in and I build a model off of it, 92% accuracy, our CNN is very nice. And that's just after 5 epochs, right? I could have let it go more, like 10, it would get like 98 maybe. But so, okay, cool. Very nice. On a base level, we're cooking, right? So let's go forward here. And then again, I stopped it because it's like, I don't want to train it. And let that go longer because I got what I wanted from that, right? And then so next test is like, let's again, like, assume that this math is true, that what I said about, like, the Rymanian zeros and that real versus imaginary, which is not proven, is let's assume that that's real, right? And then so when I do that, and then I essentially I have the model make calculations off of it, it's getting something, right? Like, to me, this is actually good. And then so this tells me that I'm on the right track. If I'm saying do nothing else with this model, but just throw in that Rymanian hypothesis, assume that it's true, and let's see what happens. And the model's getting like 33% accuracy just based off of those metrics and those measurements alone. And it's detecting stuff in there. Like, so what this is telling me is it's detecting something real. And then so what we need to do is be able to dial and exactly what the Rymanian hypothesis says, right? In that instance, dial the real structure from the imaginary structure. And then so I start working on that and towards that, right? And then so very specifically, I dial the model more, and then I like the first instance you can see here I get 55% accuracy, and then this is kind of a rare instance that happens, right? This is like what happens here is unlearning, but the model starts to converge based off of this unlearning process, even though accuracy is going down. So I essentially learned that, okay, I can tweak the dial, but I'm tweaking the dial backwards the first time. Okay, but I can tweak the dial, right? And that's what matters to me. The dial is there. The dial is real. There's something real in there that it's actually picking up on. Cool. So let's go through and let's actually try to dial it, right? And then so this is my very first attempt to dial it. And then like, pretty cool. Like, it's so this is like very inaccurate, right? Because we want, like, it's like all of these outliers that exist, which are, like, we'll call these outliers like a quarter of it is, so like maybe, like, let's say 20%, like, yeah, so it get like maybe like 80% accuracy, right? Because these outliers are what it can't actually classify properly. And then so what I do in this first instance is I just say, exactly what I described up at the top. Learn the shape learn the shape according to how you want to learn the shape, and then map the human construct based off of that shape. And then so essentially like change that shape, right? And then I run the test, and then this is like a comparison between that, like again, that like the learned shape versus the human construct. And this is bad, but it shows that this is it's again real, right? At this point, I'm just trying to get measurements that this concept like is actually like real, that there's actually like something going on here, right? And then the fact that it's measuring things, again, it's measuring something real in there. So I just need to dial in and detect like where is the line between real and imaginary, right? The Rymanian hypothesis. And then so I'm dialing that more and more, and then so within this particular model, what I do is I realize that I can put a CNN classifier or beef up the classifier of the actual like the mapper. So what I want it, and I can train it over multiple rounds, right? And I want to see what happens. And then so the shape of this gets interesting in this particular experiment. So I do this for 5 rounds, right? And let's see how the shape evolves, especially by the round 5, like or 3. Sorry, look. So look at the shape of this, like far more compression here compared to here, right? So like this is essentially what is going on is this is the original shape that the model learns, right? So I say like go find like whatever, like turn the data set into a shape that like makes more sense to you as a model, right? And it does that, and then this loss is still kind of high within that, but it's like, okay, I can do that, I can make my shape, right? And then I say, okay, now map your shape to the labels, and it's like very far off, right? And then so it's like, okay, map it, like change your weights more to match the labels. And then that's what it's doing here, and then that's what it's doing here. So essentially, it's like round 1 here is the model, like just what is the shape of this data set to you as a model without any sort of overlay, human construct overlay, and it comes up with this. And then this is okay, starting from your position. Then change your weights and then update them to match whatever the human construct is. And you can see it's massively different, right? So this tells me, okay, I'm like 1,000,000% on the right track, even though these numbers are abysmal, right? Which is fine to me, like, because it's like, all right, like I like this is what matters. Like this is very clearly different than this. And then so what I decided to do then is very simplistically, okay, if this is the shape to you, lock that, right? Like lock that becomes our centroid, our measurement point. I'm going to get rid of the centroid measurements then, and then whatever this is, like that's your centroid, and then just use that, right? And like it doesn't matter to me. And then from there, take that and then measure the human construct of the labels based off of that. And then so off of that system, this is my very first test of it, right? Which comes out beautifully. And then so in this, in this first test, I utilize a neural network as both the encoder and the decoder. And then look at this loss rate. Like the loss on learning the shape is incredible, right? Like the neural network understands that there's a shape there and that it's real, right? And this is like almost zero loss. It's like 99.8, right? It's like, yeah, there's the shape. Okay, I understand 100% the shape, right? And then I say, okay, from there, I want you to take the shape as your like whatever you think the shape is as the starting point, and then here's the labels, right? The human constructs. So here's pants, shirts, purses, shoes, etc. And then essentially your weights are frozen, so you know what that starting point is to you. Measure that against the construct, right? And then so that's what we do, and then I do it for 50 epochs, 90% accuracy just off of that. There's that's literally all that it's doing within here, right? Is it's just doing. You can look through all of this code in this entire notebook, right? And then so it's okay, cool. So I can do that, and I can get 90% accuracy. Like, okay, so can I do better, right? And then so the next thing that I do is I try to improve the model and then do essentially like more testing. The very first thing I do is I change the rather than having the neural network as the pure encoder, and I change out the neural network encoder to a CNN encoder, and then I reduce the size of the encoder, of the autoencoder. I essentially I'm trying to see can I make it speed up and go faster. These tests are taking a while to conduct, right? And then can I get also make improvements to get it to better map that foundational shape out, and then get it to blend better. And then so we start getting here, right? And then so I'm like, okay, cool. This is progress. And then same thing here. I do it. I beef up the neural network in this instance, and then what we can see is again so this is with the CNN model learning the shape, and then so it takes the learned shape and then it applies it, goes through, and then we can see here I'm getting stuff I'm getting progress, and I'm getting the model to do things, but I'm stopping. I notice that this process is stopping too early, right? So I just very simplistically, I just say, okay, let it run, let it learn, right? Like for the 10 epochs here, let it learn that, but then run for as many epochs as it needs. I set it to 98%. I set the threshold to 98% accuracy. So I want it to learn the labels, the label shape, as many epochs as it needs to understand that, utilizing its whatever it thinks is of as the original shape as the base understanding, and then run for epochs as long as it's continuing to learn until it hits 98% accuracy or above, and it does. It ran for, this took about 5 minutes to run, and then for it to converge, and then you can see it beautifully converges, right? Here is our final end result of the fashion mnist data set, which you can see is very mislabeled, right? Very clearly, you have different kinds of concepts that the model does not want to group together overall. That's why you can never get 100% accuracy on it, right? So as long as you teach the model that it's a human construct that you're trying to get it to, it'll do it. It'll just take a long time because it's a human construct, right? But so there you go. And then at the end here, we have it. This is the end result. And then so what I do here is in this last one, I stopped this last one. I ran it for 20 minutes and it still didn't even go through one epoch. So I was like, okay, that's too much, but I'll leave it in this notebook for anyone that would want it. So I made a video yesterday where I essentially went over a very souped up CNN model that had 3 attention heads, and then the cool thing that it had to me was a heat map layer for the CNN. It was very specifically on a CNN model, right? So I took my CNN classifier and then I built that into this. I took those so it has 3 attention heads and the heat layer and all that. The heat map layer, but it takes it just 20 minutes. I didn't even get it for one epoch. So it will. I'm assuming it will cook, but I can't tell you it will cook. I can tell you that this cooks, and then I could have set it to 100%. I could have set it to 99%, whatever I wanted to set it to, and then here it is, right? So the human construct neural network, as it's a class of the Zyra class neural networks, and the Zyra class neural networks very specifically work on topological geometry, quantum mechanics, and harmonic resonance is basically the 3 elements that combine within them. Within these particular models, they're also incorporating swarm intelligence and self-clustering principles. A lot of research went into this. Here it is. I hope you like the Zyra class of models, and if you like this type of content, please like and subscribe. Thank you very much.